Hello, welcome back. This is Calculus by Dr. Oz. Today, we're going to go through an exercise where we're going to practice partial fractions. This is a brand new technique that is helpful to solve certain indefinite integrals where you have rational functions in the integrand. And then the top and the bottom are polynomials. Uh, to be able to have like a good grip of the technique partial fractions, you should recall certain things from algebra. For example, uh, quadratic formula for solving quadratics, or how to factor polynomials into smaller factors, linear factors, quadratic factors. So these are the things that we're going to use in this section, and in fact, we're going to heavily use of them. So please recall those things from the algebra formula card. Let me just tell you a few things about partial fractions before we get started. And this is sort of our guideline to decompose fractions into, or rational functions into smaller linear or quadratic rational functions. So we may run into a few major cases. The first case is the improper case where the degree of the polynomial at the top is greater than the degree of the polynomial at the bottom. So for this type of problems, we need the long polynomial division. So this is another thing you may recall at this moment and check back with your algebra formula card. And if you're rusty with long polynomial division, please have a good practice of that, even though I have one example where I'm going to make you practice that in the video. And if it's not improper, try to factor the denominator of the rational function. Okay, so completely factor so that it should be irreducible. Okay. So once you're done with factoring, you may have linear terms, quadratic terms, and you may repeated terms of linear and quadratic terms. So based on what case you're in, please use that expression in 3 for linear factors and 4 for quadratic factors, because you have a specific format to follow depending on the factors, repeating factors or non-repeating factors. Okay, if there's no repeating factors, for example, if the factor is linear, go with a over px plus q. That's it. If the factor is raised to the power of 2, in other words, you have a repeating factor of 2, so you're going to have a1 over the linear factor plus a2 over the linear factor squared, and you have to stop there. Okay, so we're going to practice this a lot along the way, and let me just show you one quick guidelines that I'm going to use for the rest of this exercise and for the whole section. So this way we can practice at this moment. And this is already in your lecture notes and in your ebook. So this is the guidelines for solving the basic equation. Please put this somewhere because this involves how to proceed with linear and quadratic factors. And let's get started because I'm going to try to refer back to the guidelines and the previous slide along the way in the video. So yeah, let's get started. All right, let's start with part A. I have a linear factor at the top and a quadratic factor at the bottom. If we go back to the decomposition into partial fractions table here, first of all, I do not have an improper fraction because the top is a linear and the bottom is a quadratic, so the order of the top is less than the order of the bottom. So that's good. We don't have this case here. Okay, so, and the second case here, factor the denominator, that's exactly what we're trying to do now. Okay, so we're going to try to factor the denominator. And there are various ways to handle that, but I'm going to show my way to you. And if you like it, please go with that. If you don't like it, you can rely on to the quadratic formula. Okay, so I'm looking for factors of this and this, okay, including the signs, okay? So for example, this is 3x and x. I can factor that out, 3x and x, because 3x times x is 3x squared. And minus 1 is minus 1 plus 1, obviously. So I want to know exactly where that should go, okay? So let's put minus 1 here, or maybe plus 1 here, minus 1 here. So all I want to do here is that when I do the cross products and add the cross products, I should get down to the middle number here, or middle together with x, in fact. Okay, so let me just circle that all the way. So essentially, so I have 3x times negative 1, that's negative 3x, plus x times 1, that's x, and that should add up to the middle number that I circled with yellow. Okay, this is my way. I mean, if you change the roles of these guys here, probably you won't be able to get the middle term over there. So you have to sort of like smartly do that. Again, if this way is not the way you are familiar with, please use some other ways. And once you have this technique working out properly, so that the actual fraction, the actual factorization is 3x plus 1 times x minus 1. So this is in fact one factor, 3x plus 1, and this is another factor here. Okay. All right, so that means 3 minus x, 3x squared minus 2x minus 1 is in fact 3 minus x, 3x plus 1, and x minus 1. Okay, let me just clean this part. All right, next is to split the quadratic, the rational form into the form where you have only linear factors in the bottom, because look at that. So I have linear factors here. So I want to write this with two different fractions. And the way you do that, if you have linear factors, then in the expansion here, you have all constants. Okay, you have all constants. Okay. And m, we don't have any powers of the linear factors, so essentially I'm going to go with m equals 1. So that means I'm going to have a1 over the linear factor plus a2 over the linear factor. Okay. So let's just apply that strategy. So I'm going to split that into, let's say, a over 3x plus 1 plus b over x minus 1. Okay. So this sum of two fractions has to be equal to what I started, what the fraction that I started with. Okay, so now I have to determine a and b. So the question here, what are those guys? All right, here the common denominator to bring these two together to solve for a and b is 3x plus 1 times x minus 1. So what I'm going to do here is that I'm going to multiply the top and the bottom here by x minus 1, and here by 3x plus 1. Okay, so that I will rewrite this as a times x minus 1 plus b times 3x plus 1, since I have a common denominator, 3x plus 1 x minus 1. Okay, so in short, since this fraction here is equal to this fraction, I should have the numerators equal, right? So in turn, let me just use a different color here. So 3 minus x has to be equal to a times x minus 1 plus b times 3x plus 1. And this should be true for all x. So my next goal here is to determine a and b out of this last equation that I wrote in yellow. Okay, so let me just pause here and I'll continue that in the next slide. All right, so to find a and b, I'm going to choose sample x values. And I'm going to determine those from the roots here. Okay, so for example, for this one, I'm going to choose x equals 1, so that x equals 1 is going to cancel this term when I plug it in. Okay, so on the left, I have 2. On the right, the a term is completely gone. And for x equals 1, this is going to be 4b, and b from this pops out as 1/2. Okay. My next sample is going to be determined by this factor here. That factor is 0 for x equals -1/3, right? And left-hand side here is 3 minus 1/3, and a times -1/3 minus 1. And the b term is already gone, right? So this is 10 over 3, and this is, let's see, -4a over 3. Okay? And multiplying both sides by 3. what do you have? 10 equals negative 4a, and dividing both sides by negative 4. So that's negative 10 over 4, which is negative 5/2. Okay. So this is good because I can plug those back in those in the partial fraction that I got here. Okay. So essentially, I know exactly what A is. I know exactly what B is. Okay. So let me rewrite everything, and then I'm going to convert this fraction integrated to like the sum or difference of two fractions. All right, so this is what I have right now after I plug in A and B and replacing the rational function with two linear fractions. Okay, so the rest is just to take care of each integral by using a u substitution. Here we go. Here I'm going to use u equals 3x plus 1, so that du equals 3 dx. And here I'm going to use a different letter, so I'm going to use v equals x minus 1. And dv is going to be equal to dx. Okay? So here we go. I have negative 5/2. Okay, dx is 1/3, so I have another 1/3 factor coming along. Okay, du over u plus dv equals dx, so I'm going to pull out 1/2. It's dv over v. And these are known integrals, obviously. These are logarithmic type integrals, so minus 5/6 ln of u plus 1/2 ln v plus c, right? And you can go ahead and write down or back substitute u and v here. Minus 5/6 ln of 3x plus 1 plus 1/2 ln of v, right? X plus 1, the absolute value of x plus 1 plus c. All right, I think that takes care of part A. And I'm going to finish this video right now, and I'll see you in another video. Bye. In fact, sorry, I'll see you in the next video. That's for part B. All right, bye.